Hello, my name is Gokul Prabhu. I welcome you all to another episode of Enter Thy Minds. Today I have with me Dr. Rajeev Kini, an associate professor from School of Physics, IISER Thiruvananthapuram. Dr. Kini, thank you very much for accepting our invitation and for making this interview happen. Before I dig into some deeper questions, I would like to start from where it all began. So, could you take us through your childhood?
Well, as with most people, it all starts from the school days, right? Where I was interested in science, and I was particularly interested in physics and mathematics. But I could pursue my interests because of the freedom that I got at home, right? Unlike most of my friends, I didn't have to write an engineering or a medical entrance exam. I was allowed to pursue science, and I believe that freedom is what led to me finally ending up in IISER. So I believe it's very important, such freedom that parents give to their kids, which most of the kids miss, because with that freedom comes the responsibility, because you have the freedom to choose or pursue what you like. At the same time, that gives you the responsibility to follow your goals and achieve it. Okay, so that is very important, I believe, and I believe that freedom has and that responsibility played a big role in me ending up here.
Dr. Kenny, could you tell us more about the areas of research that your lab is focused on? And if you'll have to explain the research that happens in your lab to a general audience, how would you?
So broadly speaking, our group works on what we call as ultrafast and terahertz spectroscopy. So when you say ultrafast, it's what is fast and what is ultra fast and what is slow is relative for different people. So what we are talking about is something that happens on the time scales of picoseconds and femtoseconds. So we look at processes that happen in different materials on that time scale. And when I say terahertz is a frequency range, okay, which falls in the hundreds of gigahertz to about 10 terahertz. To give you an idea, your normal electromagnetic spectrum in the visible region, that is the white light, is about hundreds of nanometers. So if it's a green light, it is something like 550 nanometer. When you say terahertz, it is in the range of millimeters to tens of micron. Okay, so that is what one can say we do broadly. And if I want to say specifically, we are actually right now focusing on 4 different problems. Okay, I'll explain one by one, if that is okay. So the first problem is on what we call as artificial lattices or artificial structures called superlattices. So you take a material and arrange them in a periodic fashion, layer by layer, and you get what is called a super lattice, because a material is consisting of lattice, and then you create additional periodicity on that. Using that, what you can generate, you can actually modulate the heat conduction in a material, the sound propagation in a material, and so on. And even you can actually make sound mirrors for sound. Okay, so we create all that, and one could also think of making an acoustic equivalent of a laser, which is called SASER, sound amplification by stimulated emission of radiation. So that is the field, and the specific problem that we are looking in that is to see an experimental evidence for a quasi-particle which is called a photon. So you might have heard about electron, photon, and so on. Theoretically, there is a new particle which is a hybrid of an electron with a 2-level system, and which is called phonetone. So currently we are working on realizing this in the lab, because this has only been predicted theoretically. So that is one problem that we are working on. Another thing that we are working on is materials which are very similar to graphene. So you might have heard about graphene, which is like a layered material which you can actually peel off layer by layer and so on. So after graphene, people have come across this transition metal dichalcogenides, which also form like layered structures, which are van der Waals layers. Okay. Now, the interesting point or interesting problem in that is called valleytronics. So when you think of electronics, it's a flow of electrons, right? So which detects decides how your device works. Now when electrons flow or current flow through a material, you have resistance and you have I square R, heating or energy loss. And if there is no flow, then you will have cooler computers, right? So that is where people started looking at spintronics, where there is no flow of current, but they look at the spin of the electron. So if it is spin up, you will have one state, and spin down another state. So with this transition metal dichalcogenides, you can actually think of what is called valleytronics, because you look at the position or the position of the electrons in it. So if it is in one valley, it is one state, and if it is in the another valley, it is another state. So that is valleytronics. So that is something what we are currently working on. Apart from that, the same material, if you take two layers and stack on to each other, and then you actually twist them by a specific angle, you can actually modulate the properties, or you can design the properties of this material by this twist, and it's called twistertronics. So this is the other problem on transition metal dichalcogenides we are working on. And there is another class of materials that we work on, which is called a strongly correlated material system. So normally when you look at a material, you consider the electrons in a material which form a C. In a strongly correlated materials, each electron is influenced by the other electrons in it in a very strong fashion. So that's called the strongly correlated material systems. And what we are currently working on is a special class in that, which are called charge density wave materials, because the charges in them interact and arrange themselves in an ordered fashion like a wave. So that is why it's a charge density wave. So the density of these electrons modulate in space. Okay, so these are the kind of problems that we currently work on. Okay, we could actually go to the lab and I can show you some of the experiments or experimental setups that we have in the lab. Why don't we go?
Sure.
Okay, so Gokul, this is where most of the action happens, and what you see here, these white boxes are our workhorses. Okay, these are actually femtosecond lasers, which means they emit pulses of light which are only about 100 femtoseconds long. Okay, so imagine that if you want to capture a fast moving object like a horse or something, right? You probably would use a camera and you put it on a very fast shutter. So that you can do on a time scale of microseconds or so. That's mostly because it's a it's a mechanical shutter in there. But when you want to look at things like I spoke earlier, electrons or phonons or phonetone for that matter, or charge density wave, which is doing things at a much faster time scale. There are no electronic devices which will respond that fast. Okay, so we use a different technique. So imagine that you have this horse moving in the dark. It's a completely dark room, and then horse is moving, but you have a flashlight which comes on for a very tiny amount of time. And if you have the camera on all the time, you will capture the image of that only when the flashlight is on, right? So if you actually do that flashlight on and off several times, you will capture the horse moving. So we do a similar trick here. So if you want to capture these phonons or electrons moving on a very fast time scale, we have this laser which is emitting pulses only for a 100 femtosecond time scale. And that is how we capture or the motion of this, or what is happening to these charges on that time scale. So this is all possible because of these fancy little toys, which are our what do you call lasers. Okay. So this, which is called the tsunami, emits 100 femtosecond pulses at a repetition rate of 80 million pulses. So you have 80 million pulses coming out in 1 second.
Wow.
And each pulse is just about 10 nanojoules. Okay. So we use this for doing a lot of these experiments here, and some of it also goes into the box right over there, which is called Spitfire. This is actually an amplifier called chirped pulse amplifier. Okay, so this large box that you see here is the chirp pulse amplifier, and this technique got the Nobel Prize in physics in 2018. Okay, so Donna Strickland and Gerard Moreau came up with this idea for chirp pulse amplification, wherein they could actually take this femtosecond pulses and amplify it 1 million times. So this produces about millijoules of pulses, millijoule pulses, and if you look at the peak powers in a millijoule pulse coming out at at this rate, it's much larger than what is produced in a thermal power plant. So if you think about it, why this whole thing is not blowing up if it has so much of power? It's because it's only there for like hundreds of femtoseconds. So what we do with this, we take these laser pulses, and as I said, we try to see in quotes what is happening to different materials, and inside that what is happening on a time scale of hundreds of femtoseconds. Okay.
The recent pandemic situation has had an impact on almost like everybody today, be it directly or indirectly. So how has the pandemic affected the research that has been happening in your lab? Did you fall into a situation where you couldn't continue doing work because of lack of resources or lack of students working in the lab?
Really, this pandemic situation has been bad for everyone, as you know. So we were locked down, and many of my students were here, where they were kind of staying back so that they could do some work. But what happens is, as I said, this laser is our workhorse, and it went down. There was a problem with it, but the engineer couldn't come in. Neither we could get it repaired. So I had all my students sitting here waiting for this to get repaired during the pandemic time, wherein they could also not go out of the campus. That's like a really frustrating time, right? You are locked inside a small area in a campus where you can't go out, you can't do your research, right? It's a really it was really bad. However, still now things are getting back to normal. We had the laser repaired, and it's back. The guys who went home are back. So things are slowly coming back.
So you were just talking about how the current pandemic situation sort of affected the research that happens in your lab. So doing PhD is already a taxing job. What are those things you suggest to your PhD students or to your undergraduates to have a healthy, balanced work life and personal life?
Well, it is true that academic research is stressful at times. Okay, so the simple advice that I give my students is to work as a team, so that together everyone achieves more, right? So I ask them to help and support each other, and they should have not just the lab life, they should have some life outside the lab.
Sure.
Okay, they have friends outside the lab who are not, if they are doing a PhD in physics, they don't necessarily have friends only in physics. Let them go out, have friends, develop a hobby. Okay, and set aside some time away from the lab, so that they can do something outside the lab.
So, what are those things that interest you outside the lab? So, how do you keep your personal life and work life balanced? So, what are those activities that get involved other than research?
So, apart from research, music and arts interest me, and I also volunteer for the Speak Maki, and I'm a part of that organization. So that keeps me away for some time from research.
So, what makes institutes like IISER differ from other regional institutes? What are the opportunities that are available here, and how can one make use of such opportunities?
You see, the whole idea about setting up these IISERs was to integrate research into undergraduate curriculum. Okay, and so that you can mold the future scientists of the country. And so if you look at our curriculum, you would find that it's designed with this thought in mind. So our academic calendar is jam-packed with lectures and all that, but you would find that there is a 2.5 months summer vacation, as well as almost a month-long winter vacation, which the students are expected to make use of, so that they can actually get a flavor of research. And right from the first year onwards, most of the students engage in research activities, right? They become part of one of the groups, and even though they don't have a lot of background, because they are just out of school and they have come, but they still get a flavor, right? And at the end of that 4 years, the 5th year is completely devoted to research, wherein they most of the time do a full-fledged research, as well as they end up even publishing in international journals, right? So that you cannot find in any other undergraduate colleges in the country, probably. And when you look at the people who have actually graduated and then moved on to research, PhD, and so on, the feedback that we get from those places is that we have been doing well, we are doing well, and really the products that are coming out of this place are real diamonds, polished diamonds.
So we are at the end of our interview. So I'm left with one last question, which is your suggestions to students who are pursuing research, or to students in general. So what do you like to suggest to them?
So I will try to answer this the way I look at a good researcher, right? So if I'm looking at a student who wants to join me, what are the qualities that I look for in them? Okay, I generally look for 4 things. Okay, first of all, they should have a genuine interest in science. If that is not there, then you cannot actually survive in this research field, right? Because most of the time it's not something where you get a lot of money or something like that. So what you do is mostly out of your own interest. Secondly, there should be some amount of curiosity in you, right, which is driving this interest.
Yeah.
Okay. Third is that if you want to be a very good researcher, you need to have the analytical skills, analytical ability, right? So that there is a problem, you can analyze it, find the solution, right? So that skill, logical thinking, is essential to survive, right? The fourth one, I borrow from Richard Henderson, who got the Nobel Prize for Chemistry in 2017 or 18, right? That you have to be an optimist. Okay, if you are not an optimist, then you will not be a good fit in research, because in research most of the time, right, it's bound to go wrong, right? So many times you see successful experiments, but behind one successful experiment there will be 100 failed experiments, right?
Yeah.
And if you are a pessimist at the failure of the first experiment, you will leave that and go away. So one has to have that positive attitude, that optimism in them to be a very good researcher. So with that, thank you.
Yeah, thank you, sir. Thank you so much for making this interview happen again, and I hope it's going to be helpful to a lot of students and to a lot of viewers.